quantum mechanics come together, they give rise to amazing things which cannot be just described by thinking about in terms of classical mechanics, but certain things like we are familiar with, even though the origin of these kind of things like spectra are quantum mechanical, but essentially we can understand the terms of classical mechanics, and that's how we can draw pictures of bar magnets, etc., without resorting to so these are the kind of things that I'll try to tell you about. And the first would be like trying to set up the stage for the things that I want I'll have more carefully. And I'll flash some of the results towards the end. Okay, but please feel free to stop me at any point. I don't. Fortunately, I don't have a syllabus to complete. Okay, so with that, let me with trying to explain to you the last two words of the title. Matter, or more precisely, quantum condensed matter. Okay, so what it essentially means are different kinds of systems which have many quantum degrees of freedom, particularly in particular electrons and ions. Okay? And once I formulate it in this way, you can immediately realize that these are the kind of systems, these are the kind of things that we basically constitutes all the technological things that we use, starting from computers to phones, etc., which are essentially things where we use the property of many electrons and ions. Okay, and there are many kinds of platforms one uses, and the most traditional of these platforms are various materials like the semiconductors that we use for developing these processors that run our phones or our computers, any computing devices. But over the years, we have been developing different kinds of platforms. Okay, so beyond traditional materials where we use various things from the periodic table and put them together to form various kinds of materials, we have moved on to sort of make our own quantum platforms in the sense that we put simple materials like graphene, which is a single sheet of graphene, and then try to arrange them in a particular way so that we have these are often called hybrid quantum platforms in the sense that they're made out of simple things, but assembled in a way that they show interesting properties. Okay, so another set of platforms that we are gaining more and used to are these ultra cold atoms, where because we now know technologies of cooling things to pretty low temperatures, we can take various atoms and trap them in various different kinds of settings, light and other electromagnetic radiations, and study the dynamics of these or the statics of these objects, the properties of these atoms at pretty low temperatures. And this seems to reveal another aspect of physics where we have many ions and electrons interacting together. More recently, we have there have been successful efforts by various groups to develop more sophisticated version of these hybrid platforms, where you not only have the hybrid platform, but you can individually manipulate parts of hybrid platforms to realize what are called quantum processors. And basically, you can perform various coherent calculations on the or processes so-called quantum processors, where essentially these are high platforms where you can manipulate different parts of the system in different ways, which otherwise are called quantum gates. So you can do all these fancy things depending upon what interest might be, but one should remember that all these varieties of systems basically originate from interacting electrons and ions put together in various ways. Okay, so this not I mean this leads to different kinds of systems, and to emphasize that they have different properties, if you take any of the systems and try to understand the different kinds of properties that they may have, that's also a very rich set. For example, you have materials which have this weird property of superconductivity, where we have this perfect diamagnetism. This is a picture where this rotating on a magnet because of perfect diamagnetism that locks the superconductor to this situation. Okay, on hybrid platforms, the kind of things that Ankur is an expert in, we have phases which go under the name of fractional quantum Hall effect, where I think this not very nice, but if you look at it carefully, you would see that the resistance of these kind of systems, which are made out of some semiconducting wells, their resistance are to in some units, and though the systems are extremely etc. And the reason why these are so perfectly quantum, an amazing fallout of quantum mechanics of many electron systems, we now know pretty well. On the other hand, if we think about these ultra and this, for example, is a rubidium atom, one can realize various kinds of superfluids and Bose-Einstein condensates, and this was the first realization of the Bose-Einstein condensate. What you see is the fraction of condensate in momentum space, or k equal to 0 momentum. And so this is only possible because you take all these rubidium atoms and can cool them to very low temperature. Finally, this is actually a snapshot of a quantum wave function created in these Google processors. So it is supposed to describe the wave function of what is called a topologically ordered state. I'll exactly write down the wave function, and I'll tell you some aspects of this. So essentially, what quantum computer has been able to do, this I think is from 2021, was create wave function, and leading to the possibility of doing quantum manipulation with these wave function. Okay, so the whole point, realize all these very diverse things, starting from this by assembling these set of electrons and ions in different situations. But remember, the degree of freedom that one is dealing with in quantum mechanics are these electrons and ions, and the same set of degrees under different situations give rise to these various properties. Okay, so this is what quantum matter does for us, and some of these properties might be useful, some of these properties might be just interesting. We just need to understand whole lot of them to understand what and ions can do when put together. Okay, so that's what we are going to discuss for the next 40 minutes or so. Okay, so we need to break that problem down. In the periodic table, we have 100 of. If we try to understand the combinations of putting these things together, there are like infinite number of possibilities. We really don't want to have an separate understanding for each of these materials. That's not the way how we want to understand things. We want to understand how to go about solving these different many electron systems together. And this is what I like to point out. How do we go about trying to think about this problem? What are the key ingredients? And this would already take us to a very advanced understanding of these kinds of materials. So the that is, almost obvious is this issue that the quantum mechanics or all physics has an effective structure, in the sense that when we think about, it's as trivial or as naive as when we think about throwing a ball from one end of the room to the other, the Earth's gravity, but there is also sun and the moon and the entire solar system, and we really don't think about the gravitational attraction for this. Okay, the effect motion of the projectile is described by only accounting for the gravitational field of the Earth, and that too approximated by this constant g. Okay, so that is pretty. And once we want to describe things at some level of precision, this is enough. Okay, in the same sense, when you solve the hydrogen atom problem in quantum mechanics, or would solve the hydrogen atom, you won't worry about what makes up the proton, the quarks, and the gluons, and all these things. So this is what is called an effective description of quantum mechanics, that it depends upon the energy scale or the temperature at which you want to describe the system. Okay, so let's make this a bit more precise in context of things that we already know. Okay, so let's first ask, okay, what do we need to describe? Okay, so this you can go back and check with all the quantum systems that you have encountered or are going to encounter. This is all you need. Okay, so you need three things. First, degree of freedom that you want to describe. The system, if it's a hydrogen atom, it's the hydrogen atom. So the degree of freedom that you need to describe. Okay. Next, the symmetry system. Okay. So what is the situation? Okay. If I'm in empty space, the empty space does not have a reference point. It is translation symmetric. Okay. So if it is also rotation symmetric, it does not matter which direction I point to. So these kind of things are essential ingredients to describe a system. Okay. And the third thing, given that I know the degree and the symmetries, I need to know how these different degrees of freedom are interacting, obeying the symmetries of the space and time that are embedded in. Okay. So if I know these three things, I know how to start doing for the system. Okay. So let's try to make this more precise. Okay. What do we mean by saying that I know my degrees of freedom? What I mean is that I know my Hilbert space. Okay. So if I have the one, say, a spin half, which can either up or down, my Hilbert space has two basis states, up, down. Okay. If I have two spins, up, 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 down, up, down, down. Okay. So this is structured. So this HI is like the Hilbert space of the ith degree of freedom, and then I need to basically do what is called mathematical tensor product of each of these Hilbert space, basically take all the basis together to try and understand the total Hilbert space I'm dealing with. This is mathematically. If I know this, I know my degree of freedom. Okay. What about symmetries? The symmetries are basically operations on these states belonging to the Hilbert space. Okay? So since they're given by unitary or anti-unitary operators or matrices, and so they take they basically go to each spin. So if there is which flips the ith spin from up to down, then and I have 10 spins, operation of flipping all of them is like you go to every spin and flip them. Okay, so that's this operation. This is the mathematical way of saying that I go to every spin and just flip them. Okay, or if I have 10 electrons and I want to move them, I move the first electron, I move the second electron, I move the third, and so on and so forth. So this is basically a fancy way of writing this. Okay, and finally, I need to say degrees of freedom are interacting, and which is given by the Hamiltonian of the system. And the Hamiltonian has two aspects. One is that if there is a symmetry in the system, like the interaction between the electrons sitting here and the interactions between electrons sitting here are same in the sense that the interactions does not depend upon where sit. Okay, so then the Hamiltonian must not distinguish between the electrons sitting here or here, but I can get the electrons from here to here by a translation or a unitary operator basically means that the Hamiltonian needs to be invariant under translation. This is what guarantees that the Hamiltonian does not distinguish between symmetries. Okay, symmetry. And then the structure of the Hamiltonian, and this about the Coulomb interaction between two electrons. Okay, I have an electron here, I have an electron. So there is an electron operator for this electron, there is an electron operator for this electron, and then the interaction which is 1 over r. Okay, e square over r. Okay, so Hamiltonians have two kinds of things inside them. The fact that there are electrons which are described by operators. Okay, so these are like this OI is like the electron at I, OJ is like the electron at J, and then JIJ is like this 1 over Ri minus Rj. Okay, so these are operators, and this is what is called the coupling constant. So typically, you see that even though there are like 10 to the power 23 electrons in the system, so all of them are represented here. Two electrons are interacting, so it's pairwise interaction. So all kinds of Hamiltonians we have this structure that they describe all the electrons or all the degrees of freedom. Term in the Hamiltonian is like few electrons or few degrees of freedom at a time. Okay, so this is the structure of quantum mechanics that we are dealing with to describe the electron, and in fact, all kinds of systems. Okay, the structure of quantum mechanics of many body systems. Okay. Okay. So, okay. So the whole point is that these three ingredients actually depend upon the energy scale, the thing that I started out with, that and the effective, all these three ingredients can change as one change the energy scale of description. Okay, so this is leads to varieties of physical effects that I started out with. Okay. Okay. So in fact, what happens is that at high energy, okay, but by high energy in condensation, thinks about this very high energy of 1 volt. Okay, it's like the highest in condensed matter systems. Okay, so if you the system, particularly if you are trying to do experiments, make one of these materials, okay, is that you take element A, element B, all these things in a beaker and then mix very well. I mean, of course, you have to do it very in a sophisticated way, but typically you do this at an energy scale of 1 or round about that scale. Okay? So at that scale, you are extremely what exactly you are mixing, or in other words, the ions and electrons. And hereist, you are doing, you need to do what is called a first principle calculation to try and understand the formation of these energy scales. Okay? But if you want to do a different kind of experiment or a different kind of theory, or which is trying to understand the properties of the same materials or the systems at a much lower temperature, 1 millielectron volt. Okay? So suppose you want to do experiments and try to find out the properties of the materials that you created at this high temperatures. Okay? Here, what you would find is that if you try to describe the system in terms of your electrons and ions, you to make a good job of it. Indeed, because the electrons and ions are strongly interactions are enhanced at these low energy scales, one needs to account for their collective behavior, and this is where you don't know. The description is insufficient in terms of electrons, okay, ions, and instead of doing first principle calculations in terms of electrons and ions, you actually need continuum quantum field theories to describe, which accounts for the interactions. Okay? So this is essentially the point that the degrees of freedom and the effective degree description keeps on changing as you go from high energies to low energies. Okay? And this, of course, we know from other point of views. I'll come to that in a moment, but then depending upon the kind of low energy descriptions you end up with, you have different electronic phase matter. Okay? So from the same electrons, you land up in different kinds of low energy descriptions, and that is what captures these descriptions, captures different electronic phases of matter. Okay? So our present is that there are all kinds of electronic phases which can be grouped into 4 rough classes. Okay? The most well understood class is what the block, which are basically magnets, superconductors, crystals, all these kind of things, which can be understood in terms of broken symmetries. Okay? The another thing that we keep on hearing from high metals, etc., turns out to be the worst understood. Okay? Simple things, I mean, not the that conduct current, etc., the copper wires, but generically metals are the worst understood. In fact, if you are, I mean, if you work in this field, this is probably one of the open questions. How to describe metals is the burning question in the field that one needs to address. There are things which are now somewhat understood in terms of entanglement that I'll try to which goes under the name of short-range entangled and long-range entangled topological phases, which I'll try to give examples about these two quarters. Essentially, the point that one needs to try and understand is that starting with these ions and electrons, how to get to the description of these 4 classes of electronic phases. In other words, what are the rough organizing principles, or how should one go about thinking about each of these 4 classes? Okay? Because if I go back to electrons and ions, I won't distinguish between the 4 classes. All of them are fallouts of some collective behavior of electrons and ions. Okay? So as I go through different materials, how should I think about maybe a magnet or a superconductor or something like topological insulation you might have heard. Okay? So the first clue from I mean, good old thermodynamics. In fact, third law of thermodynamics, which in courses it comes towards the end of the semester and we rush through. So, but it provides an extremely useful as far as we are concerned. Okay, so what it basically says is that you take any system, any of these things that, and at high temperature, which is like high energy density, okay, and you try to cool it. Okay, so decreased temperature, temperature is like the energy density. And what third law says is that you need to get rid of the thermal entropy. Okay, the thermal entropy density. So this is the thermal entropy divided by the number of freedom you have, which is a dimension of the Hilbert space. Okay, so this entropy density needs to go to 0 as you cool down the system. Okay, so this is what all systems, more or less, this must, irrespective of what they are made, whether they are made out of lanthanum, copper oxide, or calcium, something else, it doesn't matter. It has to obey this. Okay? So this is a good place to start and ask general questions. It turns out that, yes. Yeah, okay. Yeah, that's a good question. Generically, it does not, but we now have examples where it affects. Okay, so more about this, just catch me after the talk. Okay, there is a particular reason why I wrote this way. Okay, so it turns out that we know that there are two ways of doing this, which is like reducing the entropy. Okay, so the simple way, which is the classical or the conventional way, is to break the symmetry. Okay, so think about these electrons and particularly think about their spins. Okay, so the spins at high temperature can point in any direction, and each spin can point either up or down, etc. There are two basis states. So entropy of log 2 associated with each of the spins. Okay, but happens when you cool down the spins, because find a way to all point in a particular relative direction, whether all up or up down or pattern. So out of all the patterns, it chooses one pattern and thereby breaks the, and this leads to all kinds of symmetry broken phases. This is at the heart of symmetry breaking, that you reduce the entropy by choosing one of all the possible possibilities allowed to you by symmetry. Okay, the other, which is what I'll be able to give you some example. I already read, going way slow, but which is way, okay, or the unconventional way. That's the in the title, which is basically is putting all these things together and entangling them quantum mechanics. I'll try to explain these things, and this gives to the other quarters in one way or the other, apart from symmetry breaking, all the other three quarters are described by some form of entanglement plays some role. And the reason, and as you can understand now, is since entanglement doesn't have any classical counterpart, okay, these are essentially need quantum mechanics to describe this phase. You just cannot have them classically very easily, okay, without fine-tuning generically. Okay, and this is the new organizing principle that describes unconventional quantum matter. Okay, so this is what we would like to try and understand through a few examples. Okay, so to try and emphasize the role of quantumness with something that we know very well, the classical or conventional phases, which is this left side of the picture that I showed you. And this is where all the grand successes, including the Josephson circuits that received the Nobel Prize last week, or comes from this part. Okay, So ferromagnetism, antiferromagnetism, superconductivity, all these things are because of these classical conventional of breaking symmetry. And so this is the same picture idea. Spins could have, each spin could have pointed in any direction, but the collection decides to have this pattern. So out of many patterns that can lead to entropy, it chooses one pattern, and that's how it quenches the entropy. But in the process, they break the freedom to point in any direction, which is like breaking the symmetry. Okay. So this is the topic of an advanced atomic course, that the modern advanced atomic course, which is essentially trying to describe this spontaneous symmetry breaking. So let's understand why this works, and in the process we will understand the other things. We will understand how this fails. Okay. So the comment that I'll try to make is that these ground states have trivial entanglement contained. Okay. So since their entanglement is not the primary feature, they are almost classical. Okay. So in fact, this is why we can draw pictures like this. When we learn quantum mechanics, we are electron spin does not have any classical counterpart. Electron spin is completely quantum mechanical origin. All these things are true. Okay. So you cannot have, electrons are not like balls spinning about some axis, etc. Okay. But at the same time, one can ask, in what sense valid? What am I drawing? If this electron spins are quantum mechanical objects, what am I drawing? Okay. What are these classical cartoon pictures good for? Okay. Why am I allowed to draw classical pictures for something which is as quantum mechanical as spins, with all kinds of uncertainties, etc., etc. Okay. So let's try to understand that, and just let me try to tell you about quickly about what entanglement is. And there are various ways of trying to understand this is. It's in a sense describes the non-separability of quantum systems. In the starting with the ideas that goes back centuries, Podolsky and Rosen, who found these kinds of questions fairly systematically. So I have two spins. Okay. So I need to write down a wave function or a state for these two spins. And I can write down various kinds of wave function. This is one wave function that these people way back about almost about 100 years ago, is that this is the first spin and this is the second spin. The first entry is the first spin and the second entry is the second spin. But this is a sum, so you cannot write this state as of the first spin and the state of the into the state of the second spin. So it's all mixed. This is the essence in which quantum mechanics differs from classical mechanics. In classical mechanics, you can always choose to describe the system separately. So if you have 1,000 classical particles, you can choose to describe the first. It might be incredibly hard, but there is no problem in principle. In quantum mechanics, you just do it in principle. Okay. So this non-separability of states, one of the central features of quantum mechanics, and trying to characterize the non-separability of states is what entanglement does. There are several measures of entanglement, some of them fancier than the other, some of them more sensitive than the other, but one can do this, but it is trying to characterize this non-separability. Okay. So sorry. So one can generalize this idea of two spin to an entire system. So suppose this is my, I divide the system into the left half and the right half. Okay. And this entire system is described by some state, and I try to characterize the non-separability of the state of the left half and the state of the right half. Okay. So this is a straightforward generalization of the two spin case, where to understand the non-separability of the wave function of the left spin and the right spin. Okay, so one can do the various kinds of things. The one way is to calculate the entropy, which is calculating the reduced density matrix, sort of tracing out the degree of one of the degrees of freedom in case B, and then calculating this positive definite quantity, which is called the entanglement entropy. It's basically calculating this operator log in this particular form, which you can show is a positive definite quantity. And so for check yourself that if you take a product state, both the electron up or one electron up and one electron down, this number is going to be exactly 0. Okay, so it is non-zero, a positive number only for non-separable states. The more non-separable the state is, the higher this number. So this is a monotonic character of the non-separability or quantumness. Okay, so this is called the entanglement entropy. Okay, so let's, with that lightning, go to an example and understand what it means to say classical states. Okay, so as I said that clearly the way to study quantum mechanics. So you specify the degrees of freedom. So here, which describes simple magnetic insulators, are the spin halves sitting on sides of some lattice. I've taken for simplicity a square lattice. So at every site there is a spin half which is pointing up or pointing down, so doing something. So this is the Hilbert space. There are certain symmetries, okay, which we can go into, and then there is a Hamiltonian. Okay, this is a very well studied Hamiltonian. This is one of the classic examples. This is called the Heisenberg Hamiltonian. So almost everything about this is known. So as many of you would know, that if I do take this Hamiltonian and try to diagonalize, okay, or try to find out its ground state, the exact is going to be extremely complicated. Okay, if I have n spin, there are 2 to the power n bases, and I would need 2 to the power n complex numbers to specify this exactly. Okay, and this is like a humongous job, and it's a losing fight. Okay, if you have these many numbers, and n, remember, is of the order of 10 to the power 23, there is no way you can even write those numbers later. Okay, so that, of course, we know is not the way to go. What turns out is that if n becomes large, this exact wave function becomes extremely close in particular case to a very simple function, which is like up, down, up, down. So at every so every alternate spin is up, down along some quantization axis. So this is the symmetry breaking. So the exact state is complicated, but in this thermodynamic limit, it is approximated by this, which exhibits spontaneous symmetry breaking. Okay, so the point is that this approximate state is not the actual ground state, okay, extremely close to the ground state. Okay, as far as various kinds of correlation states, but this approximate state is it does not have any entanglement. Okay, the why we can draw these kind of cartoon pictures is that this we are basically drawing this approximate ground state. Okay, because it does not have any entanglement, we can draw a classical picture responding to it. It is only because this kind of ground state, this kind of states becomes very good description of the actual state, we can describe the systems almost classically. Okay, is the reason for all the emergence of classical physics in these kind of systems, broken symmetry systems. So all the things that has been achieved and grand successes are basically by studying these kind of classical states. Okay? Okay. So, and now we can all kinds of local descriptions. Okay? But now you see that stated in this way, it becomes almost obvious that there is another possibility where the ground states cannot be described by approximately easily by these kind of product states. Okay? So, so, so let's try to focus on them. In fact, let's take a few examples. Okay. Sorry, what is happening? Yeah. Okay. So, again, I think examples teach us a lot. Let's take this example. I have a product state, but small, just add some other positions, which is not exactly a product state, which is like taking the subleading terms of the kind of state that I wrote down. Okay, so that's one possible state. Okay, a product state. Instead of taking up, down, I use any such order up, down, and so that's like a random but almost product state. So that's an extension of what we just learned. A completely different state. Okay, so the state is as follows. Okay, when I don't draw anything, it basically means that all the spins are pointing in one direction. Okay, say up. Okay, so this to all the spins pointing up. This corresponds to all the spins pointing up except one loop is given by, this loop could be of any size, it could be of any place. Okay, so all the spins sitting on those loops are down. Okay, I'm just creating the state out of just that I'm proposing. Okay, so let's take this state. Let's take the other state where I have two loops. Again, all kinds of loops. So I take my square lattice, draw all kinds of loops. Small loop, a big loop, anywhere, and whenever there is a spin on this loop, I just flip it. Okay, if there is, the spins are up. Okay, so what, all these are states, right? So if I have spins which can be up or down, I can create all these states. Okay, so I take a superposition of all these states, an equal superposition of all these states. So there are many states, countless states of the order of 10 to the 3 basis states, and I take a superposition of these. So I could have written down the Hamiltonian, and in fact, after the rock, write down the Hamiltonian for which this is the ground state, but this is a state which is very different from the one that we just discussed. Okay, so it contains all kinds of closed loops over which the spins are down. Okay, so let's try to understand the essential difference between this state. This state, if there were no small superposition, this would be a completely product state. Okay, so let's ask, suppose I try to do this calculation for this almost product state. So if it was an exact, this is my one part of the system, this is part of the system. Okay, and instead of drawing left and right, I have drawn it in this way for like just simplicity of drawing. You would see that. Okay, so if this was a exact then if I went through this calculation of entanglement entropy, I'll find that the entanglement entropy the A and B is exactly 0. But if small superpositions, I'll find that okay, it's not exactly 0, but it is proportional to the separation of the perimeter that system part A and part B. So this is what typically happens, and if you do a calculation, this is what you would find. Okay, So this is what small entanglement states give, that if you remove this small superposition, this number which I have written as hash would go to 0. So that's the, can continuously change the small superposition and continuously reduce the entanglement entropy to 0. Okay? On the other hand, if you take the loop state, the entanglement entropy, you would get a number which is proportional to L, again for the reason, but you would get a number, this additional part, which is minus log 2. And it does not matter how you divide your A and B, you would always, this changing, but this number always remains minus log 2, and to understand that. So remember that this is a loop state, okay? So all kinds of loops. So if I try to draw the loops on the system, there are three ways that loop can arrange. So all loops divide into three classes: loops which are completely within A, loops which are completely within B, loops that cross the boundary. Okay? So that's, so all kinds of loops, there are zillions of loops here, but they can be classified into these three classes and no more and no less. But now you see that, arbitrary, the loop position, the shapes, everything could be arbitrary. I have drawn squares because that's all I can draw. Okay? But these loops can be arbitrary. There is one constraint though, okay? That since these loops are closed, if a loop crosses the boundary once, it has to cross it the second time. So if I go around and count the number of crossings, I would always find crossings to be an even number, never an odd. Okay? So this very horrible looking wave function has one qubit of information which is present, which is stored like it is stored all over this, is that the number of loops that crosses any closed bipartition number. Okay? And that constraint is the origin of this minus log 2. Okay? Unless you cut loops, which is essentially changing the wave function, okay, the name function, you cannot get rid of this minus log 2. So you can change the position of the loops, you can change the division of A and B, you just cannot change this log 2. Okay? So this log 2, essentially the fact that you have chosen the topology of these loops to be closed. Okay? Chosen loops. Okay? So this is essentially, and in fact, a calculation, proper calculation taking a state like that, and this is from some old paper, you see that this log 2, in some way of plotting, you see that this is exactly what you get. Okay? Okay. So this means that if I take the product state and these loops, think about Hamiltonians for which these are ground states, one can fairly easily write down the Hamiltonian. One cannot continuously deform the random product state or the product state in this loop state, because one cannot change this log 2 continuously. Okay? So this is then the basis of describing phases on the basis of entanglement. Symmetry, all these phases the same. In fact, they don't need any symmetry. Okay? Okay, so this is an essence of what goes in all these unconventional phases. It may not be entanglement entropy, but some other measures of entanglement. Good. How bad am I doing with time? I guess so, but how long can I stretch? 15 minutes? Okay, good. So this is essentially the point that you can come up with different states which have different signatures of entanglement, cannot be continuously deformed into each other. all these issues about topological invariance, etc., that we hear are basically fallouts of this particular observation that the entanglement content in these states have some feature which you cannot change continuously. Okay? This might take the form of, as I discussed, some log 2 in the entanglement entropy or some topological invariant, etc., etc. And this is where this does not require any symmetry. And because you're classifying on the basis of entanglement, this does not have any classical counterparts. Yes. The louder. I'm half deaf.
So you have defined a homotopy path between random product state and loop state. If I'm correct, then what do you mean by you can't continuously?
Oh, no. So I'm saying that such homotopy does not exist. Okay, there is a cross. Okay, so this basically says that the thing that you are referring to does not exist.
So what is H lambda referring to?
Say that again.
What does H lambda refers to? That Hamiltonian with lambda. Yeah.
So the point is that if I try to do this transformation, there would be at least one point where this gap would close. Okay? So you cannot continuously deform this state with this state without mix this state. So this gap protects the entanglement. And what happens is that if you try to do that, at some point in between this limit and this limit, these states would come down.
What does
and
that
we will
gap
have a
refer
phase
to?
transition.
What does that gap refer to?
Yeah, so gap of some spectral gap of a Hamiltonian. So if I think about the eigenstates of Hamiltonians, they have a gap, energy gap. Okay. Yeah. Okay. So one can go into more delicate description of these kind of quantum phases in terms of entanglement spectrum, etc., etc. And there is a whole classification of symmetry protected topological phases. But let me just jump ahead of time to two examples, two somewhat different examples that I want to give, which I thought would be interesting and related to things that we to try and understand better. Okay, so and this might relevant to lots of people working here in various quantum dynamics, etc. And that's something that okay. So this is the kind of this is the same picture that I keep on repeating, and I think that this is one of the things that I would hope that you would take away from this talk, that there are these phases and many body entanglement. I just gave an example, is basically increasing. The effect of many body entanglement is increasing as you go from the symmetry protected, the symmetry broken phases to all these different kinds of entangled phases. Most entangled being the metals, etc. Entanglement plays a role which we don't completely understand. Okay, so let me give you one. Let me raise questions about about the dynamics of these phases. Okay, and description of a strongly coupled metal in the next 5 stop. Okay. So the first question that I want to describe is, if I take such a quantum system and which is strongly interacting and maybe entanglement plays, what is the long wavelength dynamics of such phases? Okay, so generally when there the degrees of freedom are weakly weakly interacting, then we have a kinetic theory description. But if they're strongly interacting, the electrons have a mean free path of the same order as their separation, and then you cannot distinguish the electrons, or just like these water molecules, they scatter before they can just move even a bit. So you need hydrodynamics to describe. So the question is that what is the nature of hydrodynamics in these kind of correlated quantum? And this is one question that has been at the forefront research of various kinds. And we know what happens when the quantum matter is in this sort of quote unquote classical phases of quantum matter, where if we think about hydrodynamics of superfluids, one takes an appropriate description of the superfluid and derive the Euler-Lagrange equations, which are called the Gross-Pitawayski equations. So one just writes down a Hamiltonian or the path integral and derive Lagrange equations of that, and that's what Gross-Pitawayski equations are, and they are supposed to describe the hydrodynamics of superfluids. And since this is a classical phase, apart from the fact that it's a superfluid, so for a smooth boundary there should not be tangential stresses, etc., this description is quite classical. So quantum mechanics hardly plays any role apart from the presence of. Okay, so the question that we want to ask is that, given these phases are entangled, can many-body entanglement change hydrodynamics, or the quantum effect can change hydrodynamics in any way? Okay, so I try to ask that question, and I want to ask this question in of a particular kind of quantum entangled phase to quantum entangled phase, which are the chiral spin liquids or bosonic integer quantum Hall effect. So these are bosons. One can write down complicated looking expressions for this. This is just to show you that we actually did some rather than just waving hands. One can derive, and there are two ways of doing quantum mechanics. One is the Hamiltonian way, which is useful for few body quantum mechanics, but then there is a path integral way, which is good for many degrees of freedom. So this is this intimidating expressions are basically path integrals corresponding to phases. Okay, so and people like Ankur would immediately realize, or high energy theorists here would immediately realize that these are the kind of phases that describes electromagnetism in our world. Okay, so these are various kinds of gauge theories which describe. Okay, so one can write down things. Okay, but suppose I try to derive hydrodynamics of these theories, which is like taking action, you take Euler-Lagrange equations, just like classical mechanics, and you try to write down the analogs of Newton's laws, and they correspond to Euler equations or systems. Okay, so suppose I try to do that. Okay, so point is that one can do that, and this is what is being done. I'll show you some results. So the central question one needs to ask is that, since these are entangled phases, where does this effect of entanglement show up? Okay, and in this particular case, it shows up in boundary conditions. Okay? So let me try to explain this to you in 2 minutes, and then I'll stop. Okay, so in classical hydrodynamics, and suppose this is the place where you put this water, which is like the pipe. Okay, so it has the x direction, it has the y direction, and the x direction is sort of infinite, and the y direction is limited. Okay, so now the fact that water cannot escape this in this direction, there is a hard wall here and here, means that at this boundary and this boundary, okay, the y component of velocity of water is 0. Okay, and the x component can be something. So what are the possibilities? So the y component is definitely 0. Water cannot escape the pipe. Okay, about the x component right at the boundary, there are two extreme limits, and regular water is somewhere midway. One is what is called the no slip. boundary, the boundary layer of water just sticks to the wall. So it doesn't slip. So if you look, so the final layer of water is just sticking to the boundary. Okay, that's the no slip limit, where right at the boundary the tangential velocity or Vx is 0. What is the other limit? The other limit is that it, okay, without any drag. So that's the no stress. So the shear stress is 0. So it does not feel any drag. It just flows past the boundary. So these are the two extreme limits. Here it completely sticks. Here it does not feel any drag at all. Okay? So this is how classical hydrodynamics works. You take Euler equations and you solve them subject to this boundary condition. Okay? Let's try to do this for this bosonic integer quantum Hall effect and try to understand what happens. Okay? So let's, you should catch on good about this. But what happens in a bosonic integer quantum Hall effect is that if you turn on an electric field, say in the x direction, okay, it leads to a transfer of charge in the y direction, and that's quantized in quantum. Okay? So if you turn on an electric field in the x direction, this is just Ohm's law. Okay? If you turn on an electric field in the x direction, you get a current in the y direction, and this is the conductivity, the conductivity which is quantized. Okay? This is a finite number. So if you try to take this initial condition, okay, and turn on an electric field, this basically says if there is a current in the y direction, there must be a velocity in the y direction. Okay? So whatever solutions that you get out of quantum mechanics must also be consistent that if you turn on an electric field in the x direction in this quantum Hall system, you must get a velocity y direction, which is related to related like this. And this sigma xy is quantized. Okay? This is a quantum effect, which is a fallout of the weird state that we. Okay? Now, once the charge reaches this boundary, the same electric field, there is a charge imbalance at the boundary. So there is an electric field. So as we know that if there is an electric field and then there is a free charge, it flows along the electric field. So the electric field has two effects. One is that it transfers charge in the perpendicular direction, and the other effect is that it moves charge along the edge. But if it moves charge along the edge, the charge cannot stick, and boundary condition is at odds with quantum mechanics. Okay? So the entire effect of entanglement, etc., is to rule out this possibility. Okay? So the after effect might seem somewhat naive or somewhat trivial, but this is this, that whole machinery of quantum mechanics is just ruling out a boundary condition. Okay? It in this other limit, and you cannot play around with this. You cannot, in classical mechanics, by polishing the surface, etc., you can go from this limit to this limit. But the quantum mechanics says that this limit is just not allowed. This quantum Hall always remain in this limit. And then you basically have to solve dynamics in this limit, and you get the solutions for the bulk theory and for the edge. Let's just focus on this. I can explain to you this, which is another piece of work actually we are writing up. You get the right hydrodynamics at the edge for these boundary conditions. Okay? Okay. So I think that I wanted to tell you about something like about the metals, but given the given I have way overshot the time here, I'll leave you with two things. Okay. This is the condensed matter group right now. You might recognize some of the faces like and this, but let me just finish with this picture and try to take questions. But I hope that you would remember this picture and to think about different ways of quantum matter and organizing principles, particularly entanglement, in trying to characterize them. Thank you for your attention.
Okay, before we go ahead with the Q&A session, we have a small, which we'll ask the chair to.
Thank you, thank you. This is particularly special, and I want a picture of this because we were classmates. So, okay, I want this picture particularly. Thank you very much. Okay.
Okay, let us switch on the Q&A session.
Yeah, just speak loudly.
Yeah.
Yes, I did.
Whoever. Yeah. Question.
In that entropy slide, you said that as we increase the temperature, the Hilbert space dimension will get to infinity. So how does increasing temperature affect?
The Hilbert space dimension is whatever it is. It's just degree of freedom. So if you have n electrons, it's the Hilbert space dimension is that of n electrons. It's just that as you increase the Hilbert space dimension, okay, entropy density, okay, which is the entropy divided, the thermal entropy divided by the number of degrees of freedom, that entropy density needs to go to 0.
So the Hilbert space dimension changes with temperature.
Yes, yes. Okay, yeah.
Hello, sir. So I want to ask first two slides maybe.
Yeah.
So there you said this symmetry breaking, right? So you said initially it was in one of the state, then it chooses to go down to one of the possible. Then means for me, I'm looking like when it is going down to one of the, for me, it is looking like more symmetric. Then how you are saying that the symmetry is getting break?
Okay, yeah. So what does symmetry do? Okay, so this related to, okay. Yes. Okay. Yeah. So let's think about the symmetry. So let's think about translation. What does it mean to say I have translation symmetry? Okay, so what it means is that if I have a system here and I translate it to this place, the property of the system does not change. Okay, so whatever is the description of the thing here, the description is equally valid here. Okay, what does it mean for quantum mechanics? It says that if I have a system described by the state psi1, and if I have the same system by the state psi1 prime, remember these are different states. Okay, These are not the same state. Okay? The properties of the same state, the properties of psi1 and the properties of psi2 must be same if there is translation symmetry. So if the properties of these two states, which are related by translation, which is a symmetry, is same, now how can I choose one with respect to the other? Okay? How can I distinguish between them? Okay? If I distinguish between them, I choose psi1 over psi1 prime, that basically that I no longer have the symmetry anymore. Okay? This is the sense in which you break symmetry. Okay? Yeah.
And another one, that limit I was asking about,
Mhm.
you took limit
Yeah.
t tends to infinite.
Yeah, yeah,
Then you took n tends to
yeah,
infinite
yeah,
and s divided by n.
yeah, yeah,
So I'm thinking of,
yeah, fantastic.
I was thinking of like s is also depending on all states.
Mhm.
So if I change, then what is happening exactly if
Yeah,
I
very
change
good.
the order?
Yeah. So the question is that suppose I calculate the entanglement, divide by the number of degrees of freedom, and take versus taking this limit. Say this limit, I'll write it here. Okay? So does this give the same result? Okay? Usually they give the same result. Okay? There are some places where we get the same result. Okay? So let's first ask, where do we get similar results? So suppose I have a Hamiltonian and I calculate its spectrum. It can be gapped, it can be gapless, all okay. So suppose I take zero limit. Okay, what does it mean to take the limit? Okay, so I take a small temperature. Okay, so this is the value of temperature. Okay, so I am being able to sample over these many states which are roughly proportional to temperature. Remember Gibbs factors and things like that. Okay, so I decrease this. Okay, that's this. Okay, and then what does n going to infinity does? N is like adding terms to your Hamiltonian. Remember, the Hamiltonian has as many terms as the number of degrees of freedom. So n changes this spectrum. So n changes this. Okay. Okay. So if I am looking at a window is changing and number of states are changing in a different way, then I have to be careful about this limit. Okay? So let's see what it means. Okay? Typically, if you know any word that you solve, okay, you would see that the spectrum is huge. Thinking about, so this is the ground state, this is the low energy part of the spectrum. So typically in simple systems like say electron hopping or okay, so this goes as one, this spacing goes down as 1 n to the power d is a dimension. Okay, so roughly like that. So if I have such systems and I calculate this quantity, okay, it does not matter how I take the limit. So for normal systems, you can check yourself that entropy is then the number of states which belong within this window and logarithm of that, right? It's entropy. Okay. So if you think about spacing, which goes as to the power some number and take log of it, divide by n, it's log n by n, and it doesn't matter. there are certain systems which we now know where the spacing E is like e to the power minus n. Okay? If I have such systems, okay, you see that even at small temperature, I have exponentially large number of states. The number of states is like 1 over this. Is the spacing, so the number of such states is like 1 over this, or e to the power n. Okay? So now if I take log of e to the power n, I have n log of some number. Okay? Divided by n is a constant. Okay? I have to be careful about limits. Okay? So if I take t equal to 0, I shrink this first, keeping this constant. So I get a number which is 0, which is what I wrote. If I take n going to infinity, I calculate this e to the power n log of e to the power n by n, okay, at a finite energy, and I get a number, constant number, and then take the limit 0. This is not equal to 0. Okay? So usually this limit commutes, but we have to be careful. Okay?
Thank you, sir.
Hello, sir.
Yes.
Firstly, thank you for the. And secondly, like, can you just go to the slide with the expression for entanglement of the loop system?
Okay. If I have a very old computer which is more less responsive than. You mean this one?
No, it's like we found an expression for that loop system, which was like some number times
Yeah,
L
yeah.
means natural log of 2. Yeah, this.
Yes.
So I just to understand this expression better. Like
Hmm.
what you said is that the presence of loops
Yeah.
introduces this minus natural log of
Yeah,
2 term.
yeah.
So that means the presence of these sort of states
Hmm.
is reducing your entropy.
Yeah.
Like I'm trying to make sense of it. Like
Yeah. So you're so two things to be concerned of, and both are equally important. This number log 2 and this minus sign.
yes.
Okay.
It's the minus sign is what is like I'm
Bothering
trying
you
to
more.
yeah.
Okay. Yeah. So that's very important. Where does this minus from? Okay. So entropy, again, roughly is counting the number of possibilities. Okay. So as I said, that log 2 comes from the fact that if you count the number of crossings, you don't know the number, but you know that number has to be an even number. Okay. So generically had two possibilities. So if I write down all kinds of states and I count open strings and closed loops, okay, and count the number of crossings, that number has a possibility of both being even or odd. But I'm throwing away open strings, okay. I'm only thinking about closed loops, which is why this number has an even number, okay.
Yes, that I'm
So the
convinced.
fact that it is choosing one of possibilities, okay, I have constructed the state in such a way that it has one possibility, which is that the number is even. Okay, so this state has irrespective of the horrible nature of the state, it has this one qubit of information inbuilt into it. It already has incorporated this information. I know for certain that this number cannot be odd. So that possibility is just not there. Not contribute to the entropy. Okay? So entropy is counting possibilities logarithmic in the logarithmic scale.
And this condition is reducing the number.
So that's why this is negative sign.
Yeah.
Okay? And since you made that point, let me just try to thing that So two states, okay? I'll write here. So I have two states. One, this random product, this product state, which has entanglement which goes as L, okay? And this loop state, which has entanglement which goes as minus log 2, okay? So you see that there are numbers sitting here, okay? Different numbers sitting here. So this entanglement or this entropy is a positive quantity, okay? So in this case, if I fiddle with this number by changing the superposition x, it's fine. This just remains positive, okay? So these numbers have to be positive, okay? These are fairly easy to prove.
Yeah, that was
Okay.
what I was going to ask after
So,
that. Like,
so then the point is that you can fiddle with this number. At worst, it would be 0. It cannot go below 0.
and
Okay.
that we would not want over here, right? Because
No,
we have
this copy defined in this way, you can show that this, okay, this is a positive definite operator. That's fairly easy to show because this psi, okay, this is a positive definite operator. Okay, so you can show that its spectrum has to be bound things, etc., etc. So okay, homework assignment. Till tomorrow, I'm sitting in this office opposite to Shambhuddha. Till tomorrow afternoon or something. Okay, so prove that all the values of this row is positive, such that with this minus sign, this number cannot. Okay.
Yeah.
Okay. So this is the first thing. Okay. So if you take that word, okay, then it is fine that if you try to fiddle around with the state, this would become 0 at worst. Okay, it cannot become anything different. Okay, 0 is like the product limit. Okay, fine. Okay. Now you see, might have a problem here. If you try to fiddle with this number too much, this threatens to become negative because you cannot change this. Okay. So
Yes.
that is the naive way of looking at it. What it really means is that you cannot fiddle with this. There is instruction to changing this arbitrarily. Okay? There are constraints on this, whatever L is. L can be arbitrary. L is just the division between A and B, right? This perimeter length is L. Okay? So that can be anything. So that says that whatever L might be, this has a constraint such that for that L into this, that must be bigger than log 2. Okay. So it means particularly setting this number equal to allowed. Okay. What it means is that you cannot take this loop state and convert it into a product state easily. That's this obstruction. Okay. So such kind of things are called mathematical obstructions of vectors. So you so we know that sometimes we can continuously rotate a into another, but we may not be able to rotate any vector into any other vector. Quantum states are just vectors, weird vectors in infinite dimensional spaces. Okay, so this is essentially a very generic statement of things that we learn for like position vectors, etc.
And by like the mathematical obstruction, you meant conditions like this, which you just posed.
You cannot do this kind of things. Okay, you can more sophisticated words like homotopy, etc. Okay, this is what it essentially stands for. Yeah,
that's all. Yeah, thank you, sir.
Okay, so for the time of interest, last one question, and then he's in, as I said, an office 12. So catch him.
Till tomorrow, me, Ankur and Shambhuddha.
So trying to see if there is a these topological phases to topological defects in nematics or so.
Yeah.
So for example, continuous transformation of topological defects would transform
Yeah.
from one defect to the other.
Yes.
And also you can combine defects to
Yes.
wipe out the defect,
Yes.
topological defects.
Yes.
Does that happen here?
Absolutely. So this is ideally we should discuss all these things. So does this come down? Yes. Okay. Oh wow, it's fancy. Okay, so the quick answer is that it's the same thing. Instead of for order parameters, you use for wave functions. Okay, so you're finding topological defects of wave functions. Okay, longer answer is that we are in physics various kinds of fields which are functions of space and time of various kinds. One is this magnetization field or the order parameters that Tapon just mentioned. But there are other things like the many body wave that I particularly mentioned. And all these things have different solutions. Okay? So one can ask that if I have an order parameter, how many different kinds of solutions it has. And so these solutions are of two classes. One smooth and rough solutions. Okay? So smooth solutions are like you can continuously form things from one to another. Rough solutions, like you cannot continuously deform. You have to go one point or a subdimension, okay, or a line, etc., where the solution looks multiple valued or ill-defined or things like that, and you have to be careful about that. Okay. A famous example of that is magnetic monopole. If you have a magnetic monopole, you cannot choose potential continuously, which is smooth at all places. Okay, you have to choose string, etc. Similarly for topological defects. Okay, so those are, but the many body wave function is also allows for such smooth and rough solutions. The rough solutions, just like in order parameter, they are characterized by the topological quantum number or the defect quantum number. These are also characterized by topological quantum number, which are exactly the topological invariants. So one can understand this in this particular case, the topological because of such rough solutions or non-deformable solutions. The example, okay, is that oh, I see. Oh, the way to figure to this is think about the same system, the square, but on torus. Okay, I'm just drawing a section of the torus, so this goes around and comes back. Okay, so I have drawn all kinds of loops, but I could have on a torus, I can draw a loop which goes around and comes back. Okay, so this is my torus. Okay, so I can draw a loop of down spins which goes. Okay, that I cannot contract to 0. One can show that that's the origin of this log 2 also.
Okay, so let's thank the speaker for answering a lot of questions, but he's here also tomorrow. So feel free to catch him if he's in his office and disturb him. I'm okay.
Okay, thanks.
Thanks.